In our previous video, we mentioned that there are two different ways we can look at a reaction. Some reactions go in one direction only, and we call that going to completion, which we represented with a single arrow going in one direction. Others are reversible, so the reaction could go forward or backward, and for that we represented it with a double-headed arrow, one going to the left and one going to the right. This indicates that the reaction can go in either direction. Later in this unit, we'll talk about reactions that go in only one direction, or go to completion. But for this lecture, we're going to talk about reactions that are in equilibrium. They don't go to completion, and these are many of the reactions that we find in the real world. In chemistry, when we talk about an equilibrium, we always say that it reaches a dynamic equilibrium. Now, a dynamic equilibrium is different from a static equilibrium. Static equilibrium might be something like when you balance something on a balance or a scale. You put one thing on one side and one thing on the other, and it just sits there. But in a dynamic equilibrium, things are changing, but in the end, the concentrations are going to be staying the same for these chemical reactions. When we watch an equilibrium in chemistry, we see that two reactions are occurring at the same time. We have a forward reaction where we have chemicals A and B reacting to form chemicals C and D. We also have a reverse reaction that's occurring at the same time where C and D is reacting to form A and B. And we can combine that all together to write A and B reacts to form C and D at the same time that C and D react to form A and B by using this double-headed arrow. And this is now considered an equilibrium equation because I use that double-headed arrow. The main piece of information we need to know from this is that the rate of the forward reaction is equal to the rate of the reverse reaction. That's all that equilibrium tells us. Equilibrium does not tell us if there's more reactants or products. It just says that the rate going forward is equal to the rate going backwards. We also know that the concentrations of the reactants A and B remain constant, and the concentrations of the products C and D remain constant, but they are not usually equal. Once in a while they're equal, but very rarely. The reason that the concentrations of reactants and products remain the same is because the reactions are going at the same time in opposite directions. So in one case, some C and D might be made, but at the same time, some A and B will be made. And since it's going in both directions at the same time, there's no change in the amount of A and B and C and D. And that means that we could allow this reaction to continue forever, but it would never change the concentrations of the reactants or the products. They will stay the same concentration. Initially, there is a change of concentration because if we have no C and D, the reverse reaction cannot occur. But once we start with A and B, it's going to create some C and D. As soon as it reaches equilibrium, which sometimes takes a little while, once it reaches equilibrium, the particles can go from being a reactant to a product or a product to a reactant, but the total amount will stay the same because the two rates are exactly equal. Let's use an example of digging a hole. As she digs this hole, the hole will get larger and the pile of dirt next to it will also increase. This is not equilibrium. This is a reaction going in one direction, where dirt is being taken out of the hole and placed into the pile. And now her little brother comes along and decides he wants to be helpful, as little brothers always are, and he starts scooping it from the pile and dumping it into the hole. And since they are going at the same rate, the filling and the emptying is happening at the same time, we see that the hole does not get any larger and the pile does not get any larger. But the pieces that are in the hole and the pieces that are in the pile have changed from one place to another. And that is what we call dynamic equilibrium. Now what happens when the older girl decides to work a little faster? So she's going to shovel twice as fast. You'll notice that the pile begins to grow again and the hole begins to get larger. Now the little brother says, hey, I'm going to go faster too. And now they're going the same rate again. Now the hole is bigger because for a short time we saw that she was able to go faster than him. But then when they reach that equilibrium again where they're going the same rate, now the size of the hole and the pile will stay the same again. The key here is that in equilibrium, the amounts may change, but the rates will stay the same. As long as those two rates are the same, they're each doing 1 scoop a minute or 2 scoops a minute or 3 scoops a minute. As long as those rates are the same, as each other, then the system is at equilibrium.